Welcome to this explainer. Go ahead and settle in, get comfortable, because today we are going on a really fascinating deep dive into the inner workings of machine learning. We're going to explore exactly how computers make decisions. It can sometimes feel like pure magic when an algorithm perfectly predicts what we're going to do next, but I promise you, by the end of our time together today, you'll see that it's not magic at all. It's just incredibly elegant logic and math. Consider this little mystery for a second. You've probably experienced this yourself. You haven't logged into a streaming service for, say, a few weeks, and suddenly, boom, you get a highly targeted email offering you a discount to stay. How on earth does the computer know you are about to cancel your subscription? Well, it's not reading your mind, it's reading the data. And the way it actually processes that data to make a prediction is the exact real-world problem we are going to solve together right now. Okay, so here's our roadmap for today. We'll start by demystifying classification, then we'll look at the customer churn example. After that, we're going to compare logistic versus linear regression before stepping through calculating the raw score, looking at the magic sigmoid function, and finally, making the final decision. Let's jump right into Section 1, demystifying classification, predicting categories, not numbers. So we are officially entering the world of supervised learning. This is a space where the model learns from examples that already have the correct answers attached to them. But what exactly is classification? Basically, it's a supervised learning task where a model learns from those labeled examples to predict a specific category or a class. Think about it like this. Unlike regression tasks where you're predicting a continuous number, like, say, forecasting that next month's sales will hit exactly $12,500, classification is all about placing things into distinct buckets. You're teaching the machine to predict a category based on past examples. Now, there are two main flavors of this task. First up is binary classification. This means the model is choosing between exactly two possible classes. Think of things like cancel or stay, approved or rejected, normal or suspicious. Just two buckets. Then we have multi-class classification, where the model chooses one class from more than two possibilities. So, for instance, analyzing a product review to see if it's positive, neutral, or negative. Or maybe sorting an IT support ticket into billing, technical, or general questions. It really just goes to show the immense versatility of these algorithms in our everyday lives. Moving on to Section 2, the customer churn example, tracking the clues. All right, let's put on our detective hats and dive into our specific case study. In classification, every piece of data has two parts, the features and the label. The features are basically the clues. It's the information the model uses to figure things out. In our customer churn example, the features might be things like the monthly usage hours, the number of support tickets they've submitted, their monthly bill amount, how many months they've been a customer, or their number of late payments. The label, on the other hand, is the target. It answers the big question, which category do we want the model to actually predict? Here, it's whether they will cancel or stay. The model looks at all those clues and learns the hidden patterns related to the final choice. So it might learn that customers with very low usage and repeated late payments are highly likely to cancel. All right, Section 3. Logistic versus linear regression, the great misnomer. Okay, lean in for this one, because we are about to uncover one of the biggest plot twists in data science. There is an absolutely crucial difference here. Linear regression and logistic regression are mathematically related, they both belong to the linear models family, but they solve completely different tasks. Linear regression is for regression tasks. It predicts a continuous numerical value, like predicting an exam score of 87, or maybe a pizza delivery time of 35 minutes. Logistic regression, on the other hand, is used for classification tasks. It predicts a probability for a class, like estimating an 82% probability that a customer will cancel, which is then converted into a final category label. So the absolutely crucial point is this. Logistic regression has the word regression in its name, but it is exclusively a classification model. I really want to permanently clear up that common confusion for you right now. It is not a regression task just because the name contains the word regression. Supervised learning describes how it learns, classification describes the task we are solving, and logistic regression is simply the specific tool we're using to solve it. This brings us to Section 4, calculating the raw score, weighing the evidence. Let's calmly guide ourselves into the math here. Don't worry, it's not as scary as it looks. The model begins by calculating something called a raw score, which is represented by the letter Z. I promise you, this is just a simple recipe of multiplying and adding. The formula is Z equals W dot X plus B. Now, if you've ever taken basic linear algebra, this probably looks beautifully familiar. It just means the raw score equals the weight vector multiplied by the feature vector plus a bias. Let's break those components down a bit. A vector is simply a list of numbers. The feature vector, x, holds all of our customers' clues, like their usage hours and late payments. The weight vector, w, holds the importance of each of those clues. A positive weight increases the raw score, and a negative weight decreases it. The dot product is just a fancy term for an operation where we multiply the matching values together and add them all up. Finally, we adjust that total result with a bias b, which essentially just shifts the baseline of our model up or down. Let's walk through our simplified customer example to make this abstract math feel a bit more tangible. Let's say we only have 3 features. The customer has 4 usage hours, 3 support tickets, and 1 late payment. The model has already learned specific weights for these. The weight for usage hours is -0.2, meaning more usage actually lowers the chance of them canceling. The weight for support tickets is +0.7, and for late payments, it's +1.1, meaning those things increase the chance of canceling, and our baseline bias is -0.5. So, following the steps of the dot product slowly and methodically. Step 1, we multiply our pairs. -0.2 times 4 usage hours, plus 0.7 times 3 tickets, plus 1.1 times 1 late payment. Step 2, we add those specific results together. -0.8 plus 2.1 plus 1.1. That gives us 2.4. Step 3, we add our bias of -0.5, and there we have it. We arrive at our raw score. Z equals 1.9. See, just multiplying and adding. Now for section 5, the magic sigmoid function. From raw score to probability. So we have our score, but what does a score of 1.9 actually mean? Well, in linear regression, a raw score is the final answer, but for classification, a raw score of 1.9 means absolutely nothing to us until we convert it into a probability percentage. That's where the secret ingredient, the sigmoid function, comes in. It is a brilliant mathematical operation that takes literally any raw numerical score, no matter how massively big or small, and elegantly shrinks it into a probability value strictly between 0 and 1. Here is the actual formula, so you can see the mechanics behind the curtain. P equals 1 over 1 plus e to the -z. Now, I know it might look a bit intimidating with the e in there, but reassure yourself that the computer handles this part instantly. Conceptually, it simply takes our raw score z and outputs our p, which stands for predicted probability. Notice how the sigmoid function perfectly handles extremes. It's like the ultimate set of math guardrails. If a raw score z is a massive positive number, the probability gets exceptionally close to 1, or 100%. If z is a massive negative number, the probability gets incredibly close to 0. It completely guarantees that our probability never breaks the rules of math by dropping below 0 or going above 1. So what happens when we run our specific customer's 1.9 raw score through the sigmoid function? It calculates out to approximately 0.87. Boom! We now know there is an 87% probability that this specific customer is going to cancel their subscription based on their features. Which brings us to our final section, Section 6, making the final decision, crossing the threshold. Okay, we have an 87% probability. But we still need to turn that calculated probability back into a real-world business decision. Remember, logistic regression gives us a probability first, but the final output of classification must be a category. To do this, the computer essentially draws a line in the sand, which we call a decision threshold. A super common threshold for binary classification is 0.5. If our probability p is greater than or equal to 0.5, we predict class 1, the customer will cancel. If p is less than 0.5, we predict class 0, the customer will stay. Our customer was sitting at 0.87, which is well above 0.5. Therefore, the final prediction is cancel, send them the discount code. Let's quickly summarize this incredible journey from raw data to our final prediction. Step 1, we gather our clues, the feature vectors. Step 2, we calculate the raw score by weighing that evidence and adding a bias. Step 3, we use the magic sigmoid function to shrink that raw score into a clean probability. And step 4, we apply our decision threshold to assign the final class label. It is truly marvelous how these simple, logical, mathematical steps combine to build such a powerful, predictive classification engine. Now that you deeply understand the elegance of logistic regression and how a computer actually places data into categories, I want to leave you with this final thought. As you go about your day today, checking your email, swiping your credit card, or logging into an app, what other hidden patterns in your daily life are algorithms classifying right now? It's kind of wild to think about, right? Thank you so much for joining me on this deep dive explainer. Stay curious and keep exploring the data all around you.